All right. Thanks for joining, everyone. I know a lot of people are still trickling in here, but we have a lot to cover today, so we're going to go ahead and get started. Just a quick reminder here. If you have any questions, feel free to throw them in the Q&A. We can certainly take questions at the end and try to answer some as we're going through here. And you also, of course, will receive a copy of the slides as well as a copy of the recording. So if you have to drop off early, don't worry about it. We'll be sure to get that sent out to you. But thanks very much for joining me. Today, we're going to be taking a deep dive into our technology and actually sharing a lot more information about how our technology works and specifically how it was designed specifically for the printing of tooling. So we're really excited to do that today. And Michael will introduce himself here in a minute. And it's great to have Michael on. You may have heard from me a lot, but it's great to have Michael here as someone new. A quick agenda here. Start with a quick introduction to Michael and I and Mantle itself. I'm sure many of you are familiar. I'm going to do a very high level process explanation, one that you've probably heard many times before if you've been following Mantle. But then Michael's going to go really, really deep into each of these different steps of the process and explain how they work and how they've really been optimized for the process. Then I never like to, have a presentation or a webinar without sharing a couple examples. So I'll talk through actually a couple new case studies that we'll be showing in IMTS and a couple other examples from our customers that have happened recently, showing why all of this really matters. Quickly introduce myself. My name is Ethan Rido. If you've been at any of our webinars before, you've probably heard from me, Director of Marketing here at Mantle, really working on content and case studies and distribution and educational content as well. And really happy to have Michael with us here today. I'll let Michael introduce himself as well.
Yeah, thanks, Ethan. I'm Michael Kottman. I'm our Director of Process Engineering. I've been at Mantle for 2.5 years, and I've worked in additive manufacturing for about 12 years with a background in material science. I started working in additive on tooling, and really glad I came back to Mantle to do more of it.
Awesome. So we're going to hear a lot more from Michael, but to really kind of tee him up here, we don't show this often, but this is really where we started. This is the first generation of the Mantle printer. It's just a retrofitted, relatively inexpensive FDM printer producing these really, really rough parts like you're seeing on the left. Our founder, Ted and Steve, the two co-founders, they saw this and they said, I don't really know what this is usable for. So how do we go from this to something usable, something that can actually add value, especially in a tooling application? Well, the answer to that is you spend a couple of years, hire really smart people like Michael, and you iterate on the technology into new generations. This is the newest generation of our parts, looking a lot better than what you saw previously, and of course, many different iterations on the machine as well to go from something that's pretty rough and unusable to really, really high quality. And Michael's going to share a lot of the work that they've done to kind of go to this level. If you're not familiar with Mantle, at Mantle, we say we are the only 3D printer built explicitly for tooling. It was designed specifically for that application. It's the only application we target. And today, that's mostly injection mold tooling. What our technology does is it prints mold inserts that are 75 to 95% complete, depending on the application, with very little to minimal user interaction. Generally, inserts require some squaring, finishing of ejector holes, and tapping of any holes. So very, very minor finishing after the printing is complete. This allows you to reduce lead times, produce tooling as little as a week, reduce the costs, reduce the amount of toolmaker time, and especially on the OEM side. And we see this real need of doing development and shrinking development timeline by being able to get tools rapidly to get actual injection molded parts in your hand. So really what Mantle enables you to do is eliminate many of the time consuming and costly steps of the conventional tool build, where you're going just from printing and sintering, you're getting an insert that's 75 to 95% of the way complete. And you're just doing a couple hours of finishing, grinding, maybe adding ejector pins, et cetera, to get it into a usable state. But we're removing the most expensive and the most time consuming steps of that tool build process. Generally, that's EDM, and we're going to talk a lot about how we've designed the technology to remove EDM later on. But going from digital file to something that's almost complete with really almost just the push of a button. Just to show a really quick example of this before we dive into some of the nitty gritty, just as a recent case study with Heiko, some inserts you're seeing on the right here. Conventionally, they had to do rough milling, a bunch of different electrodes, squaring of the blocks, drilling and tapping of holes, sync EDM, wire ejector pins, and burning of gates. They printed these inserts with Mantle. They printed and sintered them. They still had to square them. They still had to tap the holes. But those are minor finishing operations for them. They did wire the ejector pins and they did burn in the gates. But ultimately, they left all the cavity detail as printed, which was where the majority of the time went into building this tool. Of course, it's great to have a fancy technology and print some inserts, but what did it actually mean for them? They've shot over 1.5 million shots on this tool. They've saved over 2 weeks compared to conventional manufacturing, and they save 60% of the cost on these inserts compared to producing this tool traditionally. And we'll share some more inserts, some more examples later on, but just quickly wanted to share one. forefront here of why our technology is mattering to our customers. So here's really the high level explanation of our technology, one that you may have heard before. But our technology essentially combines three major steps: printing and shaping, which is happening in the printer, and then sintering, which is happening in the furnace. We're not going to get into as much software today as I would have liked. We have so much other content, and we'll do some future webinars on how the software works. But it's important to know that the software is really going to be the brains of this entire operation. It's going to generate all those tool paths automatically, no programming, no CAM. It's going to do all the sintering steps for you. So we're not going to share too much of the nitty gritty on the software, and we should do a deep dive software webinar soon. But just to know in the back of your head that all these steps that we're going to be talking about today, it's great that you want to know them, but you really don't have to worry about them because our software is going to take care of all of that for you. As you may know, our technology is pretty unique in that we are printing a metal paste. Similar to a toothpaste, we're not using any loose metal powder like other additive manufacturing methods. We're not using a filament. This comes in a tube and it's a paste material. That paste is a combination of metal powder, some binder like a glue, and a solvent. So we are printing this paste, just extruding it out of a nozzle, every single layer. Um, we're just flowing it. It's viscous enough that it can simply be printed without heating the material too much. The nozzle itself isn't, and we're just flowing this material. After every layer is printed, we come back and we dry that material. Here, we're removing the solvent out of the paste, leaving behind mostly metal powder and binder, kind of firming it up a little bit. And then really the key after that is it's firm enough to be machined. We come in with a CNC machining technology, and we come through and we refine the shape, we improve the surface finish, we add new layers that can't be printed, or that any features that couldn't have been printed with the printing process. I know I'm moving through this pretty quickly because we're going to go through a lot of this in detail very soon, but this is repeated every single layer. So every single layer, we're going to go through print, dry, and shape to build up the part. After printing is complete, put the part into a furnace. This is a sintering step. So the furnace gets just below the melting temperature of the material. We'll talk more about that later on. The part shrinks about 9%. And what the result is a dense, strong steel component. Toolmakers may be cringing at hearing me smack the inserts together, but the result is a dense, strong tool steel part like you're seeing here today. It's the result of those steps. So that's the very high level explanation that you may have heard before, the one we've done many times. But luckily, we have Michael here today to really dive into some of the nitty gritty on these things and go through these four kind of key steps of the process, explain what's actually happening at these steps, how they work, and how they were really designed for tooling. So I think the first one up here, Michael, is printing of paste, and I'll let you sort of take it from here.
Awesome. Thanks, Ethan. Yeah, so I want to start with the printing process. Like Ethan said, this is one of the most unique things about Mantle and how we designed our process to work for tooling. The paste drives, you'll see me come back to most of these topics throughout the rest of the process because our whole printing process, the whole shape refining process is driven by the properties of the paste. And so for most other binder and metal powder processing, you're going to have just a binder and the metal powder. A unique thing for Mantle is that addition of the solvent. And so the solvent gives us the viscosity where it's actually flowable and it carries the binder and distributes it evenly through the metal powder. And so that solvent's really critical. And we keep it in the paste through the printing process. And like Ethan mentioned, it goes through drying where we evaporate the solvent. That gets us to the green body density we need that I'll talk about a bit later. So the solvent's there temporarily. What's important to the green body is the binder and the metal powder. So the binder also needs to be compatible with the solvent. And so that means that it's going to be carried easily by the solvent, distributed easily in the paste, and create a uniform distribution. And then once the solvent's got, it needs to be very strong. And that's because we do our milling on the green bodies, which we'll also talk about later. The metal powder is also unique. So we use a special range of particle sizes that is designed for really close packing. That is critical for getting all the metal powder into close contact with each other, which increases our grain body density and reduces the shrink during sintering. And so throughout this process, we start with pretty low density paste. We dry out the solvent. So it evaporates, our green bodies get to a higher density than most other binder-based processing. And then we get to a sinter body, which gets to that final part with the highest density.
Just to add to that, can you quickly define, green body for just so everyone knows when we're saying green body, what we're
Yeah.
talking about here?
Yeah, great point. Yeah. So in sintering-based processing, a green body is any part that's just the metal powder that's loosely bound by the binder. And so this is kind of your work product of the shaping or casting, however you get to that shape before sintering. And then after sintering, you have your part. And so the green body is that working piece that's just binder and metal powder. Thanks, Ethan. So with the solvent and the binder and the metal powder, one thing we spend a lot of time on is making sure that we can use it in a number of different stages and that the temperature range required for the processing is easy to achieve. And so you may or may not know that we recommend storing our paste for long term, so weeks, months, in a refrigerated state. When you put our paste in a refrigerator, the viscosity is very high, which means it's very resistant to flow. And this prevents segregation of the paste during that long term storage. So, if you just even have loose metal powder or just powder and binder, it can start to segregate even just from like the slight vibration of wherever you're storing it to segregate large particles and small particles, or the binder separates from the metal. Our paste is very stable in that refrigerated state. As you start warming up to room temperature, it's still a high viscosity, so it's stable for days to a few weeks, um, and so that part keeps it from segregating while you're using it in process or during shipping. Um, but it does start to become flowable through the start of our dispense system, where we can start pushing it from that tube into the printer. Inside the printer, we heat it up to like a warm room environment, pretty warm room, close to like 90 Fahrenheit. The viscosity continues to drop, and we also start applying a shear force that lowers the viscosity further. That makes it super flowable. As it leaves the dispensing system, it provides a nice uniform layer, evenly distributes the binder and the metal powder. We don't have sputtering or chunks. Um, and then as the drying step comes in, we raise the temperature just a little bit further. So we're still in about 100 degrees Fahrenheit, so warm but not hot. Um, and that dries out the solvent, which sets apart at the shape that you dispense it into, and you get to that green body state where now it's just binder and metal powder. So that drying step, I'll talk a little bit more about. So the drying we do on every layer, um, and so we use a lamp that provides some direct heat to the part. We also heat the bed underneath the printing plate, and we heat the air inside the chamber as well. But to control the timing of the drying, we use this lamp you can see in the top right. And the reason we do this drying step every single layer instead of dispensing the whole part and then drying up the solvent is that it lets us have very low binder content, and to get rid of that binder on a layer by layer basis. And so we don't have some of the issues you have with other technologies that form the entire green body like in one step, or even on a layer by layer basis with more binder. Because in those cases, you can't go to thick wall sections because you'll never be able to get the binder out from the inside. So with our process doing this drying step, we are drying the part while it's close to the surface and then depositing the next layer on top of it. And so this incremental drying step, super important. And for tooling in particular, getting to these thicker wall sections is critical so that we're not limited to just tiny inserts. Um, and then, like I mentioned, I'll come back to a lot of the same things from the base, but it also gets us the dense green body, reducing our shrinkage and the high um, green body strength so that it's machinable in an incremental process, which I'll come back to again. I think the next slide, there's one of the parts that we printed. So this is molding insert for plastic injection molding. And this has conformal cooling in it, but it's still nearly 20 pounds. And so this part wouldn't be producible with other types of sintering processes, and with other additive processes that don't require sintering. You wouldn't get the surface finish and the part um, accuracy that we get with our process. So now at this stage, we've dispensed paste, we've dried out the solvent. So what's left is the metal powder and the binder. So this is our green body state. But we do all of that inside of a modified CNC. So the dispensing process is inside of this as well as the drying. And so being in a CNC allows us to do the shape refining of the green body. So it's a modified 3-axis system. We use a FANUC controller. Their spindle speed can go up to 24,000 RPMs, and it has an automated tool change turret. So we can switch between tools automatically. Like Ethan mentioned, all this is done by the software. It doesn't require any programming by the user. And it also moves very quickly through these steps and does automated tool length calibration. So today we're using 8 tools during the process of cutting our parts. They range from up to 3/8 inch, which we use for like the quick facing steps that I'll talk about. And they go down to a 6 thou ball mill. Uh, and we range in shape from square, bullnose, and ball to get optimal cuttings depending on the features and shapes and sizes that we're forming at any given time. Um, and so the 10th thou and the 6th thou weren't originally part of our process. Those were actually added last year. We added those after feedback from our customers that adding that finer tool would actually enable them to replace a lot of Sync EDM. And so getting that feedback, we went and assessed a lot of different cutting tools, came up with the right feeds and speeds and right processing for those steps, integrated into the process, and then released it as a software update to our customers. Um, and obviously they had to buy the tools.
These are all just standard off the shelf cutting tools, right? We don't make our own cutting tools and you can buy them from, I mean, I'm sure we have I know we have recommendations, but they're just standard cutting tools you'd use for other material.
Yeah, that's correct. Yeah, we've worked to find the right off the shelf cutting tools so that it's easy to source these tools. Obviously, our cutting of the green body is different than cutting of hardened steel, but we found the tools that work best for our process that are easy to get, readily available, and they fit inside of standard tool holders as well. And so this whole part of the process will be very familiar to people who do CNC machining. Also. Um, so how do we get to the machining portion of it? I have to go back a little bit to the dispense. So when you upload a tool that you want to have printed on a Mantle printer, the software does a lot of modifications to it to get it ready for printing. And one of those is separating that part into slabs. So every 1 millimeter slab contains 10 layers. So the layers are what I talked about before, where we'll dispense a layer and then we'll dry that layer. 10 of those form the slab, which makes the slab 1 millimeter. And then when we do the layer printing, we actually overprint a little bit of material on each layer. And then we come back and we do a very quick facing operation. So we take a large end mill and quickly flatten that layer. That gives us a really known surface height for the next layer we dispense. And so we increment through this. So right after drying, we'll go and do the quick facing operation. We'll do dispense, dry, do that facing again. Once we have those 10 layers and we have our slab, the software also adds overprint to any external surfaces. And so after we scale for shrinkage in the system, we add additional material to make sure that they're stock for cutting. And so when you have a slab that's finished printing 10 layers, it's slightly larger than the finished shape we want for the green body. And we come back through with a variety of cutting operations in order to remove that material and leave a smooth surface finish within the green body with the right size so that after sintering, it gets to the shape and size that was requested in the software.
I think this, and just to add something here, I think this answers a lot of times people will ask me a question of, what's your nozzle size or what's your layer height and things like that, which really isn't relevant to us, right? Because we're achieving our precision and our feature resolution from the cutting tools and our end mills essentially, which is that 6 thou ball end mill. So, we can essentially come back and add features in that we never could have printed because we have those tiny little tools.
Yeah, I think that's a big differentiator. It doesn't matter what our layer height is or what our nozzle size is. And because we're doing it subtractively, we actually control the tool paths where we can actually, do deeper cuts where we don't get stair stepping. So vertical walls, you can do deeper cuts. As you start going to shallower surfaces, we can do, constant cusp, which gives you a consistent surface finish by doing smaller steps. And so it's, much more like machining to a net shape conventionally where you don't have the additive problems of like, what is your resolution during printing? Good point. Great. And so, like I mentioned, we do all this machining in the green body state. So this is still just metal powder loosely bound by the binder. Because we're doing this in the green body state, there's really low cutting forces. So on one hand, that lets us do a lot of these cuts substantially faster than you would ever do on a hardened tool steel. But it also lets us use very small milling tools. So this is a 6 thou ball end mill that I mentioned we added as a result of customer feedback. And so you can notice the length of cut on this tool is very small, but in a lot of injection molding, you want to be using this for to replace Sintering EDM, which might have deep features, blind features, and really sharp corners that extend down well beyond this 2 millimeter length of cut. But because we're doing this in an additive process, we're able to do this on that slab by slab basis. So as we print and finish one slab of material, we can take the 6 thou ball and mill, which is about 2 millimeter length of cut. We can fully shape this entire layer, or this entire slab of a millimeter. And then when we finish that, we start printing the next layer. We do the refinement on that, and we can continue to step through, which lets us get that 6 thou ball and mill very deep into parts that you wouldn't be able to do in a finished part or starting from raw material. And that's what drives a lot of the use of the Sync EDM for these features. And so we get these really sharp features. If you've seen our parts like at trade shows, or if you get any of our sample kits, these are really fine resolved features. We get down to the 3 thou radii by using the 6 thou ball end mill. We can form really deep features into the part, and we don't really have those aspect limitations that you get with trying to do this from just CNC. But we get it without the added complexity of those other operations to get these features conventionally. So after you finish the contouring steps, you move into a sintering process. So this is now moving outside of the printer and going to the furnace. And the result of that printing process, you'll take out a build plate, and the build plate will have our green body on it. It looks like the part you uploaded to our software, but it's compensated for shrinkage in the sintering. So it's about 9% larger than what you anticipate as your final part. And again, this is just the metal powder and binder. The solvent's already left the part. Um, and we put this into the furnace. The furnace also comes as part of the Mantle system. It's a vacuum furnace, and we use a nitrogen environment for the sintering process. So you do need it to be inert because any oxidation will prevent sintering. Um, in a lot of cases, conventionally sintering would be done with argon or hydrogen, but we've designed a special retort inside of this furnace that allows us to use nitrogen as the inert gas.
Can you just quickly explain the retort and what it is?
Yeah, of course. Yeah. So in a furnace, you have heating elements, and the heating elements are resistively heated in order to provide the heat for the furnace. But they don't provide very even heating inside of the furnace. And so a retort absorbs the heat from those heating elements, and then it redistributes the heat to be more even inside of the retort. So the heating elements are on the outside. Just inside of that is a retort. And then inside of that is where you'll place your parts. And then the unique design for us is how we flow in the nitrogen gas, collect it in the exhaust, and do handling of things like the thermal debind.
Awesome. Thank you.
Yeah. And so when you get our furnace, it comes pre-programmed again with the sintering process for different materials and different sizes of parts. Um, it starts by pulling a vacuum in order to get rid of all the oxygen, and then we start flowing the nitrogen in to create that atmosphere. Uh, we do a controlled ramp up to the first temperature hold, which is the thermal debind. So this is where we hold the part in order to remove the binder from the metal powder. That binder comes out as a gas. It goes through our exhaust. It gets trapped and captured in the furnace exhaust. And after that, you just have your metal powder left. And so we do another controlled ramp to our maximum temperature. This is over 90% of the melting temperature of the alloy that you're sintering. We do not form a liquid during the sintering process. So it's different than a lot of processing where you form a liquid, you shape that, and then you cool it down. In our case, this is a completely solid state process. And because we start with that high green body density, we're able to get to that metal part and retain a lot of the surface finish, the accuracy of the part, and get this densification process underway, but not losing the benefits of doing the shape refining beforehand. This process, is driven by a lot of different forces like surface energy. But over time, it'll get to the highest density it can achieve. And so we hold at that temperature until we reach that density, which is about 96%. And then we do a very controlled cool down in order to cool down the part at an even pace. We continue to flow nitrogen to protect it from oxidation. And so this total process takes about 32 to 48 hours, depending on the alloy that you're sintering and the size of parts and number of parts you put in there. This is a batch process. So if you have multiple Mantle printers, or if you've printed parts on your printer for a while and you have a number of green bodies, multiple green bodies can go into the furnace at the same time. And so that allows you to have like really good efficiency on this process. So you put in the green body after the time passes for sintering, you get out your final part from the Mantle process. So this is your sintered body. it will have shrunk about 9%. That's why we do the compensation on our side with the software. And the results of this dense steel. So you get to that 96% density. As sintered, you'll have, hard material with excellent surface finish. So it's about 1 to 3 micron RA or a D2 surface finish for SPI. The accuracy will be about 1 thou per inch. And so this is, substantially better than a lot of other pure additive processes. And you get to retain those sharp details, the crisp edges, all the shape refining we did at the green body state still comes out in the centered body. And today we have H13 tool steel, which is a workhorse for many types of molding and forming, as well as 420 stainless, which is used a lot more for corrosion resistance and applications where there's concern about impurities like medical.
Awesome. And to explain that accuracy, the reason it scales with size, that's due to the sintering step, right? Because we can machine a green body to machining tolerances, but how closely we can predict that shrinkage is why it scales per inch, correct?
Yeah, that's correct. Yeah, the machining side very, we get the accuracy you expect out of a CNC on that green body. Um, and then it scales with size because sintering does depend on how thick your part is and how easy or difficult it is for voids to migrate to a surface. We do calibrate our paste on a per lot basis, and we get large lots of paste. And so, most of our customers are using a single lot of paste for months at a time to print. And we can actually calibrate each batch of paste for its specific shrinkage. And that allows us to get this really high resolution beyond what other processing requires, where you might have a different amount of binder loading in different segments too. So that uniformity carries through here, and that's how we get that accuracy.
And 9%, I believe, is like half of what other sinter technology normally is, which is why the tolerance is so much better, just because predicting 18 or 20% is a lot harder than predicting 9%.
Yeah, so that's totally true. That's why we work so hard to get that green body density, and so we get to this high center body density with less shrinkage. The other difference, because of us getting 9% shrink compared to 18 or even up to like 40%, depending on the process, is that allows us to do that machining in the green body state and then retain those features all the way through the sintering process. If you're shrinking 20 or 30%, doing shape refining in the green body state doesn't save you much time in the post processing because you won't be net shape on any of your features and they'll all require extra finishing. So that's pretty unique in our process and why we were able to do it as a hybrid system.
Yeah, absolutely. And kind of to add to that point here of, is this compatible with traditional? And like we said earlier, our technology ideally gets you 75, 95% of the way there. We've had customers take things right out of the furnace and stick them right at a tool. But if on the other side, we've had customers touch every face when they need to for really high end, medical things of there. So important to know that if you do need to, you can absolutely machine grind, drill, tap. You can polish it to an A2 texture weld. We have a lot of customers who'd like to do kind of a blind test with their machinist to see if they can tell RH13 versus their traditional, and all of that is totally compatible. And I think this is something that there's some future content here for us to produce around this and to show different examples of what the finishing steps were and how it worked. Going to quickly wrap up here with a couple of examples of people doing this. This is a great example of just some of that really crisp feature resolution that's possible with us. This is a threaded component. They printed these inserts in 2 days, so the whole insert was finished in less than a week. The threads were left as printed. All they had to do was square and tap holes, and it was fully functional MPT threads. They gauged and sealed properly. And of course, what does that mean for them? 2 weeks of savings, and you can see just how crisp those threads are there on that tool that were left as printed, which is always great to see. Um, Another example here, they were calling this a banana core. It's a slide component that was used to mold actually the inside of this plastic component you're seeing here. A 3-day print saved them 75% of the cost in over 4 weeks here because they didn't have to do finishing to that feature detail there. Additionally, Heiko has a pretty capable tool room, but they said they would have had to send these tools out of house to be made if they hadn't had the Mantle system to get them there. One more quick example from Heiko before we move on. Just a good example of a pretty complex tool, which again, you're seeing this theme of deep ribs here. Parting line was also at 15 degrees, so they would have had to do a lot of EDM and a lot of not just the burning, right, but the designing of the trodes, the machining of the trodes, the programming of all of that. And they didn't have to do any finishing to the feature detail. They estimated they saved 40 to 60 hours of just sinker time and very, very minimal finishing after printing. A good new example from Nicolay Plastics, a customer of ours. Um, this is a housing component. They printed both of these inserts you're seeing here, the same example as we were showing earlier with the green body. They printed these in about 5 days. Of course, that's fully unattended. They also incorporated some conformal cooling into this insert, which is always a, kind of the icing on the cake, we like to say, because they're generally saving time and cost even without conformal. So why not add that example in? And also, they saved over 2 weeks with these inserts as well. This is one of the new case studies we're working on and we'll be showing off at IMTS coming up soon. Um, One more quick example you've probably seen before. But this is a great example from Westminster Tool working with a medical device OEM. This is a representation of the part just because it was a confidential component. But the inserts required over 40 swipe by shutoffs, as well as a contoured parting line. The owner of Westminster Tool said there wasn't a chance that this was going to work with Mantle, but the team wanted to try it anyways, and the result was pretty astonishing in that they printed the inserts, both inserts, in about 6 days. Of course, totally unattended time. They sintered them in another 2 days. So in about a week, they had inserts through the sintered state. So in that almost finished part, they did a lot of finishing or some finishing to these inserts, about 2.5 weeks of squaring. They hard milled a couple of the primary vents. They EDM'd the ejector pin holes. They tapped water lines and bolt holes. They hard milled just a couple of the difficult swipe by areas. And the ultimate result was they had production representative molded plastic parts for their medical device OEM customer in just 4 weeks, which they estimated was a 50% lead time reduction compared to 8 weeks. Another really big advantage here was the ability to save 65% of the manufacturing time compared to traditional, and the ability to have their tool makers be working on other stuff while the printer was taking some of that out of the way for them. We're just gonna wrap up here. I know we're a little bit over time already, but I have a quick poll here as we certainly want to be doing more of these webinars in the future, but would love to hear, what would you like to see more of in the future? What's going to be helpful for you? And we certainly like to keep these educational as well as um, case studies, examples, finishing, etc. So feel free to vote for as many of these as you would like, and certainly going to be doing more of these in the future, and maybe even convincing Michael to help out, hopefully. So or great to see. Pretty, and if you see a couple others, if you said other, feel free to throw it in the chat or in the Q&A. I would love to hear what you had in mind, but I'll leave this open for just a couple more seconds here, and then we can wrap up with just a couple last thoughts here, and of course we can take a look at the Q&A. There's just a couple more seconds. Awesome, pretty great attendance here. Awesome. Um, One thing I wanted to note, if you're going to be at IMTS in Chicago, largest manufacturing trade show in North America, we'll be in the West Building Level 3, booth 433136. It's a huge show, bunch of different buildings. So we'll be there showing off a bunch of applications, parts, etc. Would love for you to stop by and say hi, and we can show you some of the stuff in person and talk a little bit. The other thing I want to quickly offer is a lot of times people are asking, great, this looks interesting. What does it cost? How long does it take? I want to understand what this would take with my inserts and if they're a good representation. Now, this is just an example of things we generate all the time for people during evaluations. How long the part would take to print? How long would it be in the furnace? How much paste would it consume of those paste Michael was telling us all about? What's the cost estimate? We have a pretty sophisticated cost model that is very, very easy to run. So if you're ever interested in understanding if I, had a Mantle machine, what would it cost for my inserts? You can either click this link up here above or go to this website or send me an email. We'll be more than happy to take a look at your inserts and run some of this analysis for you. It's really easy for us to do. But thank you so much. I'm sorry we went a couple minutes over here. Hopefully this was valuable to kind of take a deep dive. We shared a lot more information here than we have before. And thank you very much, Michael, for joining us, certainly outside of your everyday responsibilities. So thank you for participating, and thanks for coming, everyone. Feel free to shoot me an email if you have any questions, thoughts, comments. But we'll go ahead and take a look at some of the Q&A. But thanks for coming, everyone. I'll just kind of go from the bottom here. Your question about tolerances and part size options. Like, you want to quickly speak to, max part size and the sort of tolerances.
Yeah. So today, the max part size is close to the one that we showed, that's about 20 pounds. It's possible to print parts that are larger than that, but because of that part accuracy that Ethan and I talked about, where it scales with part size, we might start going outside the tolerances when you get above that 20-pound range. The print size that's printable, so our build envelope is 220 by 220 millimeters in X and Y. And then it goes to 167 millimeters in Z. So it's about 8 inches by 8 inches by 6 inches. That is, we do have to pre-scale the part and add the overstock to it. And so the 8 by 8 by 6 is close to the right size for what could be uploaded. You don't have to use that build envelope for printing a single part. You can use that build envelope for printing multiple parts at the same time. And that can be very cost effective because things like drying don't scale with the number of parts or size of parts. So the more parts you put onto a plate, the faster you can get them out as a batch. Um, but yeah, we're typically printing things. They can go very small, down to less than an inch by an inch, and then up to things that are 6 inches by 6 inches. Those are pretty successful for us today.
Awesome. Another question here about conventional tooling. Shrink rate is applied during mold design. I assume this is for the plastic piece shrinking as it cools. Um, how do we account for that? Or when you're designing a tool in Mantle, how would you compensate for shrink rate and for this? I assume you would design your tool equivalently to how you would design it for traditional, of course, leaving stock where you may come in afterwards and do some grinding or, in a couple examples I could have shared. We have customers who have, they print just a little extra and then they come in and they burn, do one burn instead of doing five burns to get that super critical shrink rate. Or, I assume we're talking tenths here or thou to adjust for that shrink rate. But anything to add there, Michael, of what you've seen of how people can account for some of that stuff?
Yeah, mostly customers are dropping in their existing tool design process. So we have customers who use really sophisticated software to model the impact of cooling channels, and they can use that today to design their tooling to perform optimally to account for shrinkage in the mold. The one only thing that I think comes up often is for designing of cooling channels, because we're printing it in this three axis system, we'll typically teardrop the top of the cooling channels, which is a lot easier to close. We can print circular cooling channels of a certain size, but we typically recommend the teardrop process.
I think you can see that here.
Yeah, that's a good
With
example.
these, yeah, and then just kind of undersize the inlets and outlets to drill and tap those anyways. But
Yeah,
that's a great
exactly.
example.
But yeah, otherwise it's, whatever process for the tooling today will work for designing tooling for Mantle. And we have design guidelines to also help with things like teardrops.
Yeah, and I'm sure it would also depend on the application and the tolerance you need, whether or not you print it at size or you leave a little bit and just know you're going to have to come back and do a little bit of work. A question about the final hardness of inserts after they come out of sintering.
Yeah, the H13 comes out as centered at about 40 to 44 Rockwell C. And so it's right in the zone of a lot of tooling use. The H13 can be heat treated up to, I think, 50 to 52 Rockwell C. Um, and then the 420 stainless steel as centered, we don't necessarily, it's typically heat treated even in the rock condition. But as centered, that comes out in like the high 30s. And then we recommend a double temper, which gets it to about 50 to 52 Rockwell C as well, which improves the corrosion resistance. And it's the preferred state for that material.
Right. Just taking a look here. Oh, question about, I guess this is ties directly in terms of durability. How durable are these inserts compared to traditional? Are they just for prototyping? One thing I would share is we certainly have customers and other people have run these inserts into the millions in H13. I don't generally, of course, it would depend on the application of what you need. You can repair the tools if you need to, but it is a raw tool. It's a tool steel. It's durable. It can run millions of shots. Anything to add there, Michael, about what we've seen on the durability side?
No, I think you're right. Like we see it as a lot of shots, and it is the tool steel. And so, as you get to like high wear condition, we've also done welding tests. You can re-weld edges and then grind them back to the final finish. So you can treat them in the same way you would do normal repair operations. You also just reprint the insert and swap it in because you can save that as a digital file, print it in the future, and replace that worn component. But we do test it, and just like you can do the milling, finishing, EDM, you can also weld it back up as you go through those high cycle wears.
Yeah, great. One last question here, which is probably a good one to wrap up on. It's a question of, do any of our customers or do we use this technology for printing just parts rather than tools or end use products? I would say the answer to that is that we are incredibly focused. And that is one thing that I think both Michael and I and a lot of people that work at Mantle love about Mantle is that we are fully dedicated to tooling. And we know that this is the application that we do best on. We feel we do it better than anyone else. We want to spend all of our time making our customers successful in this range. I think a lot of additive companies have tried to do a lot of different things and go after every single application and sadly not do any of them overly well. We have one that we do well, and we're really focused for that. And the added benefit of, like Michael said earlier, one customer said, "Hey, it would be great if you had a 6 dial ball and mill." We implemented that, and now all of our customers are using it. So the work that Michael does isn't just for one niche application; it matters to all of our customers, which is why that's something that's pretty unique about Mantle. And I think what a lot of us love about Mantle is our focus on tooling. I don't know if you have anything to add there, Mike. Not that you couldn't, I guess, but we generally don't entertain those inquiries.
No, yeah, it's totally right. And yeah, on the development side, we're focused on how do we make tooling better and faster. And so, like even this year, we've released over 10% print time reductions to our customers. And so we're continuously updating our systems in the field and making the systems we'll sell in the future better. And so, what I described is, our process and our materials, but we're still developing this process to make it better for accuracy and feature resolution, but also print speed and make the cost more attractive for more applications.
Yeah. Awesome. Well, thank you everyone for coming. I apologize that we ran a little bit over. We're certainly going to send out a recording as well as a copy of the slides, but thank you for spending 30 minutes with us this afternoon. Hopefully this was valuable and you learned something new. And we certainly dove a lot deeper than we never have. And thank you for joining us, Michael, as our special guest this week. And we hope you'll come back.
You bet. Thanks, Ethan. Thanks everybody for
Awesome.
coming.
Thanks everyone. Have a great rest of your day.